Hey guys, today we're going to look at waves in terms of harmonics and in terms of instruments. So this lesson is going to focus on standing waves. And standing waves are waves that are reflected, so their original wave and the reflection match up. So this video shows that a little bit better. So a standing wave is when you don't see the wave actually traveling, but the reflection and the original wave perfectly match up, so you see this just oscillating pattern. So in this diagram or in this picture, this is considered the first harmonic. This is the second, the third, the fourth, the fifth, and the sixth. So what you can do is count the number of crests and troughs in order to determine which harmonic is present. Okay, so the first harmonic is one crest, the second is one crest and one trough, etc., etc. These relationships occur in both string instruments and wind instruments. So for string instruments in particular, when a string is plucked, a standing wave is created. This wave has a node or an area of no motion and an antinode or an area of a maximum motion. So keep in mind, here, this would be where we would have no motion. At the very, very top of the crest or the very, very bottom of the trough, that is where we would have the maximum motion. This diagram shows the fundamental frequency or the first harmonic. So just like in the little video on the previous slide, the first harmonic has one crest in it. So this is what it would look like if the wave were allowed to continue. That's the first wavelength, but this is the length of the actual string involved in making that noise. So string instruments have nodes and antinodes, no motion and maximum motion, and this diagram is the first frequency, the fundamental frequency, or the first harmonic. So harmonics are, by definition, the series of frequencies that are multiples of the fundamental or first frequency. So that sounds kind of weird, but when you sing in harmony with someone, you are singing a sister frequency almost. That person might start at 100 hertz and you're singing at 300 hertz. It is a multiple of 3. Specifically, the second harmonic, the wavelength is being halved, so your frequency doubles. On the previous slide, this string had only a half of a wave in the picture, so the wavelength would have been 2 strings. The wavelength goes down by half, so the frequency is going up by 2. In the third harmonic, the wavelength is again decreasing. It is becoming 1/3 of the original length, so the frequency is being tripled, because remember, these are inverse relationships. So the first harmonic is 1 crest, the second harmonic is 2 crests or 2 troughs, the third harmonic is now 3, so we would count 1, 1, 2, 1, 2, 3. The frequency of the harmonic depends upon 3 things: the length of the string involved, the speed of the wave in the string, and the tension of the string. And we can calculate the harmonics using the following equation. So please note, Fn, this n is just an indicator. It is not actually being used in the calculation. This second n is the number of frequency you are calculating. So if you're calculating the third harmonic, it would be F3, or the third frequency, and you would plug in a 3 at that location. And then the second half of the equation, velocity divided by 2 times the length, because the fundamental harmonic, or the first harmonic, the wavelength is twice the length of the string. So this equation, n times velocity divided by 2L, is how to calculate the second, the third, the fourth, the fifth frequency for a given string instrument. Wind instruments work the same way. The only difference is, instead of having closed ends or areas of no motion at either end, they have opened ends. So here we have a half a crest and a half a crest which is the total of 1 full crest. Here we have half, 1 and half, which is a total of 2. Half, 1, 2 and half, which is a total of 3. So this is the first harmonic, the second, and the third. They just happen to be open-ended air instruments or wind instruments. Both ends are free to vibrate, which means that both ends are an antinode. And the waves have to fit in this weird configuration of having both ends open, or a half a crest or a half a trough on either end. But since it is the same relationship, and this is 1 crest or trough to 3, the equation is the same exact equation as the string one. So again, the V is the velocity of sound in air. The L is going to be the length of the tube instead of the length of the string. And the N is the number harmonic we are solving for. Now the last one is a special scenario. This is a closed-ended wind instrument. This would be like if you've ever blown across the top of a partially empty pop bottle. You would get that weird sound of vibrations. Well, the bottom of the bottle where the pop is standing, like imagine this flipped on end, that can't vibrate or it can't move because there's not an opening there. So this is actually a little bit different. And this is only half a crest. So even though this is the first harmonic, I'm only seeing half a crest instead of a full crest. This, I have 1 full and 1 half. This is actually the third harmonic. 2 fulls and a half, this is actually the 5th harmonic. When it comes to closed-ended pipes, you may only have odd harmonics because one end must be closed and one end must be moving. So in a closed-ended pipe, we have the same number of nodes and antinodes. But in the open-ended pipe and the string, one of them would have more. We would either have 1 more antinode or 1 more node. So only odd-numbered harmonics can be present, because if I double the frequency, I would need to have a node on both ends, and that's not physically possible. So this is going to affect our equation a little bit. It's going to be similar to the previous one, but one number is changed. Since the wavelength is originally 4 times the length of the pipe, we have to divide by 4 instead of 2. So remember how I said I saw half a crest? Since it wasn't a full crest, it needed extra length in order to have 1 full wave. So this bottom number now is going to be a 4 instead of 2. But again, the ends act the same. This is actual math. The third harmonic, you would plug in a 3 here, but then F with a little 3 is just the indicator. But remember, you will have trick questions. There are no even harmonics here. You may be able to solve for the mathematical value of it, but that doesn't mean that it exists because it's not physically possible. So keep that in mind. So here we go. Here's our practice problem. Determine the length of an open-ended pipe required to produce a fundamental or a first frequency of 480 hertz. So we have F1 equals N times the speed over 2L. And F1 is 480, N is 1, the speed of sound in air is 343, 2L. So since this is a 1, I can just ignore it. So I have 480 equals 343 over 2L. Multiply both sides by 2L, and I get 960L, and that gets this out of the bottom, equals 343. Now divide both sides by 960, and my length is 0.357 meters, or 35.7 centimeters. Now, what is the value of the second harmonic of that same pipe? So what I can actually do is the same equation, F2 equals N times V over 2L. Now I know the length, so F sub 2 equals 2 times 343 over 2 times 0.357 F2 equals 2 times 343 over 0.714. F sub 2 is 2 times 480, 0.39. So F sub 2 equals 960.78 hertz. Now this is the long way of going about doing that. Technically, since it's the second harmonic of a pipe, all I had to do was take this 480 and multiply it by 2, because first harmonic times 2 is the second harmonic, and my answer was 960. So rounding issues gives us the decimal place. Either way, both are acceptable answers. So in class, we are going to talk about harmonics, hopefully figure out any questions or concerns that you have, and then practice with these equations. So I'll see you in class. We can go and do that.